next to before break? The buddy system. Okay, so you're going to have a couple of scattering lectures this week. Kurt's going to talk about scattering models on Thursday. Is that right, Kurt?
Yeah,
Tomorrow, yeah. And Emmanuel will be talking about beam transmission after this. Okay. So I thought I would just start with the sort of basics of scattering in the similar way that we talked about the basics of absorption. So, okay, so you remember this. Our thin layer of material which has some fraction of scattered radiant power coming out of that thin layer, and there might be some absorption, and we can measure transmission. And if we ignore the absorption, then we can go through this similar exercise where we look at the scattered radiant power relative to the incident, and that would be called the scatterance, which is just a term that people don't use, really. And then we can derive the scattering coefficient, which is similar to we did for absorption. It's the scatterance per unit distance. So it's the loss in that thin layer, delta x. And going through all the math that we did yesterday in the exact same way, we can derive the scattering coefficient, which also has units of per meter. So I leave that to you to do, right, as a homework assignment. No. But the question for you is, how would this measurement be different than the one that we had for A? There's going to be differences, right? Like if we wanted to measure, we could certainly measure this, but our loss term is really different. Why? Because of the angle, right? And it turns out that the angle of scattering can tell you an awful lot about the material in the water. And so being able to resolve that is really instructive. And so we're going to think about how you might measure scattering, the actual scattered scatterance in different directions. Okay, so first I want to just talk about what gives rise to scattering. And so we're back to this electromagnetic radiation of the oscillating magnetic and electric fields, and they're perpendicular to the direction of propagation. And so we had, and they're going to be polarized, and we have polarization lecture week 3 for Ken. Ken is giving a polarization. You're giving a lecture on polarization? Yeah, oh yeah, okay. To be continued. So if we think about this dipole, and you put that dipole in the presence of an electric field, it's going to oscillate, right? And when it starts to oscillate, and I got these really old pictures from my friend Darius, but I think they're kind of interesting if I can orient you to them. This is the plus, this is the minus, okay? And then these little arrows are showing the oscillation, okay? And these are the electromagnetic fields coming out from that oscillating dipole. And so you have the oscillation out, the oscillation back, the oscillation. This is like growing. And then finally, you can see you have all of these waves propagating away from this dipole. And ultimately, you get to this image, which you probably can't see is that if you look at the arrows on this flow field here, it's going in this direction and this direction. And so you can begin to think about that as the image up here where we have the positive and negative oscillations of the electric field. So this would be negative, this would be positive, this would be negative, this would be positive, right? And so it's radiating out. And so we could look along this direction and see this oscillating fields coming away from this oscillating dipole. And so when we think about that, we have to think about how that is differently going to arrive from, say, an oscillating dipole that is small relative to the wavelength of light, or a particle that is large, that might be comprised of multiple dipoles within that particle. And they're going to, each one of those oscillations is going to interact with other oscillations, right? So when Emmanuel talks about me theory and me modeling, you're going to have to think particularly about the size of the particle in terms of its diameter and the wavelength of light, which is on the order of hundreds of nanometers. Because different things happen to this oscillation as you span the relative diameter to wavelength. The other thing to think about is when we can think about it with regards to electronic states. And so if we think of elastic scattering, we have this quantized energy from a low electronic state to a higher electronic state. And the elastic scattering, what is the energy, how much energy are we going to get out of an elastic reaction? All of it, right? That's the whole point of being elastic, is you've got a certain amount of energy in and a certain amount of energy out. And so we can think about this as the loss of exactly how much there was a gain. Okay. Now we do have something called, say, Raman scattering, which I think we're talking about next week, where that same energy that came in can be released to a higher vibrational state of the ground electronic state. And so you can see that the energy contained in this type of scattering is a little bit less, right? Because it's going to a higher vibrational level. And if it's less energy, it's a greener photon, right? So if you started off with blue energy coming in, you would end up with a longer wavelength coming out. And so I believe Ken is going to be talking about Raman scattering. And I will be bringing a spectrofluorometer where we can actually put water in the fluorometer and measure the Raman scattering, the signature. And it's really well predicted by theory what that shift is. And I think, are you going to talk about anti-Stokes?
Don't remember.
Okay, well, I took it out of mine, so I'm putting it in yours. Okay, so, all right, so back to this oscillating dipole. All right, so, and we've got this thing here. Now, we were just looking in this direction and looking at how we arrive at the oscillating electric field in this direction, but we can begin to look in other directions, right? And you can imagine that we could sketch out what that field would look like, and we could also look in the forward direction, right? So directionality of scattering becomes really important. And it turns out that for small particles, you can get this type of intensity of scattering of, so here's your small particle. It's much smaller than the wavelength of light, and each one of these is indicating the intensity of scattering in that angle, assuming that you have incident light here. And you can see that it's a little bit smaller at that 90 degree where the oscillation is occurring. And as the particle can get a little bit larger, you see that there's a little bit more enhancement in the forward direction. And as particles get to be very large relative to the wavelength of light, they get much, much greater in the forward direction. Okay, so we have to think a little bit about the geometry of the measurements or the geometry of the process. And so if we think about light passing through this thin layer, and we have scattering at some angle theta in this direction, we also have to think about it in a spherical sense. So if we think in terms of scattering at this angle, are we also thinking about this angle, and this angle, and this angle? Because they're all at the same zenith angle, but they're at very different azimuth angles. And we often assume an azimuthal symmetry because it makes the math easier, but in the ocean, we can't. And Kurt has spent a lifetime thinking about the asymmetry, right? And having to think about all of the different angles and keeping track of those, because sometimes you can't assume an azimuthal symmetry. And so really what we'd want to do to figure out what the scattering at that angle is to integrate around this entire solid angle here in the sphere. And so we call that the solid angle, the omega. So a note about solid angles. I always have to rethink about this every time. So if we think about a circle, and we have some arc length, so it has a radius of r, and we've got some angle in here, that's some theta angle. then the arc length is r d theta, right? So now if we put this on a sphere, we can say that this area of the surface of that sphere is dA, right? It's going to be some distance here times some distance here, and that will give us that surface area. Well, let's do the easy part. Let's do the r d theta, right? So that's the length of that side of the surface. And then if we had this area down here, it would be a little bit easier because we'd be at the distance of a radius from the center. But we're not. We're at some angle theta. And so if we want to look at the length of this, well, it's going to be represented by some d theta, right? But is the length here the same as the length up here? No, why not?
It's a sphere,
so it's narrowing as we get to the top, right? And so we have to maybe project that down onto this plane and think about what this distance is going to be so that we can scale it. And so if you go through the math, we find out that that length is going to be r sine theta d theta. So the sine theta coming from here, the d theta coming from this length here. And so the area, if we multiply this, is sine theta d theta, right? D phi. And so that is a solid angle. And that will just be a number that or a term that you should remember. The sine theta d phi is the solid angle d omega. And it's representing this solid angle here, which I've drawn as a square, but you could really think of it as a cone. Okay. So when we think about scattering now, since it has this angular dependence, we call it the volume scattering function. And the term that we use is beta. And it's a function of the zenith angle and the azimuth angle. And so it's the amount of power that we get. So if you have an incident light coming in to this thin layer, and we can think about this little volume in here, we have a certain amount of light coming in. It's the amount that gets scattered into that solid angle. And if you think about the terms that are coming from this, we have some power per unit solid angle that's emanating from some volume given by this, some volume of water. And it has been illuminated by some irradiance that is coming from this direction, right? So if we break that term apart, we can say, well, I'm going to pull that volume out and make it bigger. So we can think about the amount of irradiance that is impinging upon this volume on this surface area, okay? And we're going to call that surface area S. So we don't have an A in there, so it's not absorbance or absorption or absorptance. A surface area. So we have the power per surface area. It's got units of micromoles of photons coming in per meter per second. And then we have the volume term. And the volume is just the surface area times this length here, so dsdr. And then we have, let's see, so if we put that all together, we have the radiant power over the solid angle per volume per irradiance. Okay?
Say that again.
Mm-hmm. We've taken this definition of the volume scattering function. So we have the amount of power scattered per solid angle here, arriving from some volume, this volume in here, dsdr, that is arising from this incident irradiance, which is the incident radiant power per surface area. So its units are what?
Units of beta.
Yeah. What are the units of beta? Well, those will cancel, right? Those will cancel. Solid angle. Steradian. Solid angle is steradian. per meter. Okay.
So is that just sort of the definition of volume scattering function up there, and then all right, and then
Yep.
we go here's
And here's how all the pieces fit in. This is what. So if we end up with units of per steradian per meter, and that's beta. And beta is a function of theta and phi. Just thinking about units and thinking about what this looks like in terms of, we're measuring at a single angle here of a whole sphere. How do you think that's going to relate to the scattering coefficient? You're going to have to integrate it, right? You're going to have to integrate it for all theta and all phi, right? Because if you do that, that will be the solid angle per steradian, and you'll end up with per meter. So conceptually, you could measure the scattering just by looking through your little thin layer and seeing what gets transmitted, and everything else is scattered, right? That's what the AC9 does, essentially. Or you could measure the scattering for all angles and add them up. Okay. Yes.
Can you just conceptually explain what the solid angle is?
Yes. The solid angle, so if you have your volume here and you have a sphere conceptually around you, the solid angle is the cone for which you would have scattering, some discrete amount of scattering coming out. So it's not in the same way that we have a little piece of length around a circle, we have a little chunk of area around a sphere. And this little chunk of area is represented by theta and phi, by a little piece of d theta and a little piece of d phi scaled by the sine of theta. And so if you had sort of the infinitesimal lengths of this area piece and you added them up over the whole sphere, you would end up with the surface area of the sphere. Is that helpful? Mm-hmm. Yes, for radius 1, absolutely, yes. Is that more?
Yeah.
So I think of it sort of conceptually like an ice cream cone, right? You could have this be any shape you want. You just want to make sure that you add them up around the entire sphere. But it's essentially looking towards either light emanating out of it or light coming into it, depending upon if you're measuring scattering or you're measuring a radiance. So if you're measuring radiance, you measure radiance also with a little solid angle detector. And in fact, the C side of the AC9 has basically a little solid angle also that it's measuring.
And the unit would be steradian for the solid angle.
Pardon?
The unit for the
Steradian, yes. Steradian is a solid angle. Yes.
So what, for example, is the steradians, the number of steradian for half an hemisphere? Let's think I'm measuring all the light getting into my table from the top hemisphere. How many steradians would that represent? 2 pi. Why 2 pi? You're right. It is 2 pi. But just to, how did you get to 2 pi? Surface area of a sphere is 4 pi r. We're doing for a unit sphere, so there's 4 pi steradian for a hemisphere. So half an hemisphere is 2 pi. So the lower hemisphere is also 2 pi steradian. Just to get a little bit of a sense, because once you start integrating, you see pi's coming in. And so you want to have a sense of how many steradians you have.
How many radians in a circle? Okay? Or one tau. That's fine. Okay. So if we simplify this, we end up with 1 over the radiant power times the derivative of the radiant power per length per solid angle, right? And so that's where we arrived, since these units cancel, that's where we arrived at the units of per steradian and per meter. Okay. So if you plot that, and now I am going to assume some azimuthal symmetry. So we can plot this, or I'm just plotting it for one angle. We can look at the volume scattering function per meter per steradian as a function of theta. And this is a log scale. And this is a typical volume scattering function for the ocean. And what can you tell me about the scattering as a function of angle for this bulk measurement?
Almost all forward scattering.
It's what?
Almost all forward scattering.
It's almost all forward scattering, right? In the first 30 degrees, it drops by over an order of magnitude. So, and it's really small in the back. So let's think about this. You have light coming into a medium. Most of the light goes in this direction, and only a very small portion is in the backward direction. Does that make sense? Yeah, right? So there's not much backscattering. So if you look down at the ocean, and this is an average volume scattering function for the ocean, and most of the light is coming down, most of the light goes down, and a small portion gets backscattered. All right, so when you start thinking about the albedo of the ocean or the reflectance of the ocean, ignoring surface reflection, only a small part is coming back to our eyes, right? Most of it goes down and heats the ocean and provides light for photosynthesis, yeah.
Can you send a small plot?
So then the small plot is the first 3 degrees, right? And so you can see that it's really peaked in that forward direction. Okay. And if we integrate under this curve, and we did it in around the whole solid angle, which I'm assuming there's azimuthal symmetry, we'll get the scattering coefficient. And remember that this is the solid angle, sine theta, d phi, so we'll have to do the whole integration. And it looks like this. So we go from 0 to 2 pi, all the way around, like this, okay? And we go from 0 to pi in theta. Does that seem right? So I'm sweeping out half a sphere, right? And then I'm wrapping it around. And do I compass the whole circle? Yes. Okay. Just want to make sure. Sometimes acting it out can help you conceptualize it. You got that? Yeah. So you can see it now, right? Instead, what I did was and then wrapped it around. Okay, excellent. All right, so that's the forward scattering. There's a little bit less side scattering, very little back scattering, right? So that's the angles that we're looking at. Okay, now of course, if we integrated just the first 90 degrees, that would be this hemisphere, and we would call that what? Forward scattering. And if we integrated this part, we would call that backscattering. And backscattering is really important to us in this class. Why? That's what's essentially making it out of the ocean. You could imagine you could have multiple forward scattering events that would get you around, but there'd be a lot of absorption probability. So most of what we see, and Kurt will talk about models for reflectance that rely very heavily on backscattering and making some assumptions about the fact that the forward scattered light really does not contribute to what comes out of the ocean. Okay, yes?
Why is it like 90 degrees and this is like 180? So why do we call it 90?
0 to 90 degrees. And then azimuthal symmetry wraps you around, but it's essentially what comes out of the entire hemisphere is the forward scattering. Well, in this case, the forward scattering, if light's coming down from this way. In this case, the light is coming this way because they were thinking about it in sort of standard terminology where you have the zenith being 0 here. But when we think about it in the ocean, the sun is above us, so we're looking at forward scattering in the downward direction. Backscattering would be the upper direction. Okay, so you integrate in one hemisphere, you get forward scattering. Integrate in the other hemisphere, you get backscattering per meter. Okay. If you wanted to think about if you wanted to be able to compare the angular distribution, because this is just one, and honestly, I modeled it, so I didn't make this measurement. Kurt's going to talk all about measurements. But this is not constant in the ocean. It varies. Of course, it's going to vary as a function of the concentration and the size of the particles and the composition of the particles, wavelength, all of those things. But if you wanted to be able to compare the angular distribution of the scattering for material that you had different concentrations or different efficiencies, you could take this volume scattering function and divide it by the area under the curve, so that then you could look at different shapes of the scattering coefficient. And we call that the phase function. And it has a little tilde over it. It just means you've basically removed the magnitude so that you can really just compare the angular distribution. Okay, and I'll show you some examples. And Kurt will talk to you a lot about how to model this phase function, because it turns out it's really important in radiative transfer. You remember it showed up in the equation of radiative transfer, that angular scattering from one angle into another angle. Okay, and of course, we have to do this for every wavelength. Okay. All right, so the things that are going to influence scattering, again, it's this important relationship between the diameter and the wavelength of light, the refractive index relative to the surrounding medium. We'll talk about this. It does matter whether the particles absorb also, because there's always a competition between absorption and scattering. Particle shape is important. I think Emmanuel will talk about the impact of shape on some of these scattering models. And of course, to first order, concentration of particles drives the concentration or the intensity of scattering. Okay, so back to Rayleigh scatters. So if we look at the phase function or the volume scattering function for particles that are small relative to the wavelength of light, where there's relatively uniform scattering in both directions, our volume scattering function looks something like this. It's symmetric about 90 degrees, which, remember, when we had the incident radiation on the dipole, so the degree of oscillation, right? Where it's oscillating, it's a little less. And we can also plot it this way, where we look at this is 0, and so this would be a 10-degree zenith angle, 20, 30, and 45. And so you could draw your volume scattering function like this, where the length from the scattering center is the intensity of the volume scattering function. So the length to this line is that height. The length to this line is that height. Okay? And what you notice is that on this diagram, they show the scattering vectors for green light and for red light, and they're different. Right? So for small particles, the scattering is lower than it is for green light. So, and you can imagine where blue would be, right? So blue light would be even higher scattering, right? So really particles scatter blue light more intensely. Okay. Yes.
So that would be for one particle.
Mhm. Yes. Yes. So this is the behavior for one particle, and then if you had randomly distributed particles, you could get this. Now, you will be doing a me-scattering lab on Friday, and things get really funky when particles get big. Yeah? Mm-hmm.
So in this one, it looks like side scattering is your really lowest.
Is your minimum.
Did we see that in the volume scattering function in the past slides?
Not when you have one for mixed particles. So this includes large particles.
This is right like a.
This is just a chunk of ocean water.
Okay.
And so now if we break it down and say, what do the small particles look like? Well, this is the contribution by small particles to the volume scattering function.
By small.
This particle is small relative to the wavelength of light.
Right. That, and how are we defining that? Some kind of ratio.
Yes, the ratio of the particle diameter to the wavelength is much smaller than 1.
Is much smaller.
Yeah, but then there's this sort of zone in there.
Sure.
Yeah.
Okay.
And so you have to think of it as a continuum.
Yeah.
Okay, so if you get to larger particles, and you think of these larger particles as being comprised of multiple dipoles in there, and that the radiation actually sort of penetrates into the particle, we can think about it a little bit differently. And so people talk to them as me-scatter, or refer to them as me-scatterers, but I think it's better to think about them in terms of particles that we can model with me theory. They're just particles. They're just large particles that are large relative to the wavelength of light. And so what we see if we do sort of a ray tracing type of exercise, if we have this big scattering particle here, and we've got all of these different positions of incident rays on this particle, a lot of stuff can happen. And so what do you think can happen? Don't look. Yeah, so you can get reflection off the surface. You can get refraction in the particle if it goes in the particle.
A combination of.
Some combination of the two. It could be, yeah, it could make it out the other side.
Is that diffraction or?
So you can get diffraction away from the particle. So the light gets bent, even though it hasn't touched. Yeah. So here's a little diagram. So refraction is the bending of light as it goes to the particle. Reflection is off the back, and diffraction is bending around the particle.
So diffraction is what accounts for the more forward.
Yes, thank you. I think it's the next slide. Okay, so if you have a large particle, and this is a single particle, and you have incident light, this is this very weird scattering behavior, the volume scattering function for large particles. And you can see it's really enhanced in the forward direction. And you also, for a single particle, can get these very strange lobes. Now, when you have randomly oriented particles, some of them are spherical, some of them are not. They have a range of size distributions. They may all be large. This can smooth out a little bit. For monodispersed or single-sized particles, you can get these very strange lobes, and you'll get to do that on Friday. But the upshot is that most of the scattering is in the forward direction, yes.
So conceptually, the whole backscattering could be considered as reflection or just as specific?
Well, you could have internal refraction and back out too, right? Because how would you measure it? How could you discern it if you were just measuring the scattering in the backward direction, right? It would be really hard.
Can you explain the diffraction part? Is
Yep.
it like a diffraction grading?
We'll get
Like-
there.
Okay.
Yeah. Okay. So let's think first. We can use Fresnel's law to think about reflection and transmission. And so if we think about that we have some incident amount of of energy, and there's some transmitted and there's some reflected, right? We can assume conservation here. And it turns out that the amount that is transmitted or reflected depends upon the index of refraction, which we'll define, and the incident angle of how that energy is impingent on the surface. So one of my favorite ways to show this, because it just seems so intuitive to me, is to think about waves. Think about electromagnetic waves propagating. And is anybody in band, marching band? Okay, good, excellent. I was never in marching band. I have no talent in music. So if you imagine you have lines of marchers, and they're marching, well, we'll start on this one. They're marching down a street because there's a parade. My kids were just in a parade. They were marching down the street. They were not this lined up. But you can think about each line of marchers as being the crest of a wave, or the high point of the electromagnetic wave. And you're supposed to maintain a certain distance, I hear, between you and the row behind you. And so you're marching along, and everything's great, and everyone's playing their music, and then suddenly the road ends. I don't know why. I don't know what town this would happen in, and you end up in sand. What? Okay. So you're marching along, everything's great, and all of a sudden you end up in sand, and you're marching slower, right? Because it's harder to walk in sand. And so that first group steps off and slows down, and the group behind it is still on concrete, and they're speeding up. So eventually, everybody gets off, but what you notice is that the wavelength has shortened, right? They slowed down, everybody caught up, and so now they're still marching separated, but they're closer together. If you could imagine that the concrete came back, what would happen to that first group that stepped onto the concrete? They would speed up, and they would increase the distance between them and the line behind them. This is how traffic is supposed to work, right? You slow down at a stoplight, you speed up, you slow down. You get on the highway, you get off the highway. Everybody stays a safe distance apart. So that's great. That's refraction. You've changed the speed, the propagation speed. Now, if they were not paying attention and instead of walking parallel to the interface and we're coming at an angle, you could see that this person in this line that steps off slows down relative to the person next to them. And so as you propagate through off this angle, you can see that the marchers end up at an angle different from where they started on the concrete, right? And then if you can imagine that they made it onto another road here, they would speed up, and this first one would speed up and get ahead, and you would end up back at the same angle that you started, okay? So that's the simple explanation of refraction. So materials have different indices of refraction, meaning that they can speed up or slow down light that penetrates through them. Okay? And that's what causes light to bend within a particle. Okay? Is that good? All right. Okay, this is probably the worst animation I've ever drawn, and I'm really sorry. I'm precluding this. Okay, so it turns out that the wavelength in the medium is proportional to the wavelength over the index of refraction. And so if we have this particle, we have some wavelength of light coming in, and if this has a higher index of refraction, and this is just, imagine it's a perfect sinusoid, and that the wavelength is shorter than this. It shortens up and then retrieves its original wavelength, okay? And diffraction just moves around. And then, if it was coming in at an angle, it would bend, and then it would recover, but it would be at a different physical position. And so now if you imagine light coming into these particles, coming in at all different angles, or hitting the particle at all different points relative to the angle of incidence, then you have to think about constructive and destructive interference of how all of these wavelengths, all of these rays of light interact on the other side. And so you'll have bands where they constructively interfere and bands where they destructively interfere. And that can give you that sense of those lobes, okay? All right. So it turns out that if you measure the scattering intensity in the small angles, and we're talking about this part out here, if you, and see, this is a really bad, you guys can't see this. See, this is what your graphs looked like this morning. This is the amount of scattered intensity if you take into account transmission and reflection. This would be sort of the volume scattering function equivalent of just transmission and reflection. And if you included diffraction, it's the long dashed line, which gives you all of this, right? So most of that forward scattering is diffraction. And if you model with me theory, you can predict that pretty well. And you guys will get to do that on Friday. So then that is most of the scattering in the forward direction, is that diffraction. So if you did these experiments in physics where, you could do the slit diffraction experiments, but if you took, let's say a bunch of circles, little tiny circles, and you looked at the illumination pattern on the other side, you've illuminated them, you can see a very large bright spot here and then some concentric rings around it due to diffraction. If you had rectangles and cylinders, you see a really different pattern, right? And so that says that it actually makes a difference what shape your particles are in terms of whether the light that comes around that's diffracting around the particles, how those all come together on the other side in terms of constructive and destructive interference. Okay. Oh, and then this one is just looking at a candle flame through a fogged piece of glass, just for your pleasure. So if we're going to measure the volume scattering function, can we assume azimuthal symmetry in these two cases? Not really, right? So particle shape and man, are you going to do anything with shape in the Me Lab? You're going to talk about it. Okay, good.
But if they're randomly distributed,
It shouldn't matter. Yes,
in all directions.
except for in this beautiful case.
Right.
Except for in this beautiful case.
Yeah, I mean, this is probably the not random.
Right. And if you think about the particles that are in the ocean, such as phytoplankton, there's some question as to the orientation of them in a flow, right? So if you have flow, they line up, right? Or if they're sinking, they have a different orientation. So I don't know, it's just something to think about. Could you use the diffractive pattern in something dominated by phytoplankton to tell you something about the orientation of non-spheres? I don't know. Be a fun project. Okay, so that's the basis for the design of the list. How many people have worked with a list or heard of a list? A couple. We working with a list? Are we going to work with a list? We're working with a list on next week. Next week? Okay. Yeah. So the list is a really clever instrument, and you'll talk about it, but I just want to show you very quickly how it works. You've got a beam. You've got an area of sample that it's illuminating. You've got particles in here. You've got a really awesome, cool lens. And you've got a detector. That's a circle, but I'm showing you from the side. So it's got a small solid angle here for which you can measure light that is perfectly transmitted. And then it's got a series of concentric ring detectors. No, I'm not drawing it quite well. You get the point, right? So if I look along this axis, you can see that if I had light, well, if I'd drawn it correctly, if I had light coming in here, that didn't get scattered, it would go right through and get detected as transmitted light. If I had instead some scattering, it's going to project into one of these angular detectors, and if I had some very big scattering, it might go into this one, right? So there are different angles here. One angle, two angles. The detectors aren't completely circular. They detect on certain chunks of that sphere. So what it allows you to do is to measure beta of theta within the first 20 or so degrees. And so it's measuring primarily diffracted light as a function of angle. And it turns out that that is tremendously determined by the size of the particles, and not so much by the composition of the particles. Why? Exactly. Because if most of the signal in the forward direction is diffraction, and diffracted light has not entered the particle, it's not sensitive to that. Now, there is some light that will show up that has gone through the particle, but most of the signal is relatively independent to the composition and gives you the size distribution. So that's why the list becomes a really interesting instrument for size.
Can you like figure out what the shape of the particle was based on the...
So, when the instrument first came out, they basically did a bunch of simulations and created a bunch of lookup tables for various size distributions and the retrieved pattern of diffraction for random spheres. Now they provide you with an estimate for non-spherical particles. And so yes, the answer is yes. And are you going to touch on that?
We probably touched on that, but we have now an empirical inversion that's based on natural particles.
You can't really tell anything from the signal.
Not from the
We
signal.
can't tell from the signal.
No, you just know what your uncertainty is between the spherical and non-spherical
And
approximations.
you can't tell from the signal because the signal is, you get one detector that
Yes.
integrates on the azimuth, some part of the azimuth. You don't get.
Yeah, so maybe this part, they have the detector on this one, and maybe on this part, the detector's on
And
that
so with a
azimuth.
full detector does not separate different parts of the detector.
Actually, the detectors are a fourth of a circle. So you've got, let's say the light is not azimuthally symmetric, but it's gonna be sort of, it might be like this kind of shape if there's non-spherical particles, or it's a laser coming in, whatever. So really, to get this whole shape, you only have to measure a fourth of that pattern, because it's got kind of like a cosine symmetry. So the detectors are actually a fourth of a circle, and then you can multiply by 4 to get the answer for the full circle.
But you can't resolve this.
No. And you assume
You
that
can't resolve it. no.
Right, you can't resolve it, but you're measuring a representation of it.
Assumption is that all the shapes are identical.
Yes, exactly. Okay, so then the question is, for particles that have an index of refraction that's different from water, the medium that they're in, and if that's what is going to impact scattering, we should know something about the index of refraction of particles. And so here's a nice study from Dariusz Starmski, where he looked at how the index of refraction of particles, bulk particles, change as a function of their carbon concentration, their internal carbon concentration. And what you find is that for particles, as they increase the carbon concentration of the cell, the index of refraction changes. And so you can see that it's, relatively significant from 1.04 to 1.0, almost 1.07. And so the composition of the material has a big impact on its scattering. Okay. This is a really nice study from Mike Twardarski in 2001. I think this was one of his postdoc papers, where he looked at the backscattering of particles. So this is the backscattering efficiency. So all the light scattered in the backward direction divided by the total scattering coefficient, so that you could just basically look at the ratio of total scattering that is in the backward direction. So this is 1% is scattered in the backward direction, 2% is in the backward direction, 3%, etc. This is the size slope. So what's the size slope? Well,
I would cover it tomorrow.
okay. So what do I do? Do I show you? Do I not show you? So basically,
Twice, it's always good for
okay, if you have a steep slope, say -4 versus a flat slope, which would be, say, -3.
What's the axis in it?
This is the diameter, and this is the number of particles per,
That's concentration.
yeah, concentration. So if you have a steep slope, what does it tell you about the relative contributions of large versus small particles?
More small particles.
More small particles. If you have a flatter slope, you have more large particles than you had before. Not more large than small, but a bigger contribution of large particles. Okay. And so that's what's on this, is this indication of sort of the size of the particles. And what he found was that the particles, he made a bunch of measurements of the backscattering in different waters, and he found that places in the water column that were dominated by phytoplankton showed up down here with relatively low backscattering efficiency. Detrital particles, like NAP, tended to show up with about 1% efficiency of backscattering. And mineralic particles tended to show up here closer to 2 to 3%. So mineral particles are much more efficient backscatterers than are phytoplankton. So if you take two water bodies where you have maybe the same number of particles, the same size, and one is mineralic and one is phytoplankton, which one is going to be brighter? Yes. Even if the absorption properties were the same. Okay. The contour lines are lines of constant index of refraction. So there's a very big difference in the index of refraction.
All based on mean theory and theory.
Yes, which is perfect. Okay, so the problem, the effect of absorption on this is that you have so we talk about the index of refraction. The real part is what slows down light as it enters into the particle. The imaginary index of refraction is defining that exponential decay in the amplitude that we derived yesterday, right? So that's what describes the attenuation of light entering into the particle. And so if light enters into a particle that has absorption properties, it reduces the probability of scattering, because once you have absorption, it's gone, right? So if we take this particle and we draw the absorption, I remember you guys did that yesterday. So, oops. Right, it's getting attenuated. And so what is that going to mean for particles that enter into this if it was 100% absorbed? Yeah. And so for particles that enter in, they don't get scattered in the forward direction, nor do they get scattered in the backward direction. And so phytoplankton at certain wavelengths are really, really strongly absorptive. And so their backscattering at those wavelengths where they absorb is really small. And so when we start talking about models of backscattering and the spectrum of backscattering, people say, oh, well, there's going to be some spectral slope to that. And we'll talk about later you guys will learn about that and how it's function of size. But what if this particle happens to absorb? What if it's a phytoplankton? Right? What if its absorption spectrum, and these are not on the same scale, but looks something like that? What is going to happen?
No backscatter in those peaks.
Yeah, in these areas, right? And so what if you measured here and here? You'd say, oh, look, backscattering's flat. What if you measured here and here? Whoa, look at that. Backscattering has positive slope. Okay, so it really matters the wavelengths that you pick for your backscattering spectra. And if you pick one, which one are you going to pick? Oh, we tend to pick out here where there's no absorption, right? But now we have spectral scattering, spectral backscattering sensors. What are the wavelengths, Emmanuel? Do you have any that might overlap? Yes, you do. Okay. All right. So some of the constituents. I would like to take, can I take a few minutes? What time am I supposed to end? I'm supposed to end at, I think we should, before we jump into this is just going to be talking about different particles, but I think we could take just a 5-minute break and like get some oxygen. Okay.
I've learned all of this stuff before. I was applying it to dust particles in space.
Right, right? Yeah. It's all the same. Well, because the physics is physics, right? Yeah. It's just different. Yeah, and I think the difference is sort of the fluid nature of the water, that you have all of the molecules scattering around it, whereas in the atmosphere you have relatively diffuse gas and small particles. Yeah. Yeah.
I'm going to understand my colleagues in this telling me their work much better now.
So I work with a snow guy, and he does a lot of modeling of snow, which is basically ice particles in air. And so he just says, oh, well, but scattering doesn't depend upon wavelength. It's always flat. And I was like, whoa, wait, what? But for him, his air pockets are large relative to the wavelength of light. His ice balls are large relative to the wavelength of light. And so they completely ignore the scattering effects. But then he's like taking that model, which is fine for snow. And he's like, oh, so we can just run my model in the ocean. I was like, oh, I don't think so. Right? We have things that scatter blue light, preferentially because they're small. And so he's just, he literally was like, I need to come back to this and think about it. And then he came back and he's like, oh, right, from atmospheric, I remember, blah, blah, blah. But it's like the thing that he holds so dear because it's the easy approximation for his model, he can't use. So
if all the particles are aligned, the scattering, to tell a bit more about their shape, right?
if they're all aligned and if you can resolve
It resolves that pattern.
that pattern as a function.
So are there particles in the ocean that are easy to align in a layer? Like artificially?
So yeah, I think you could definitely align some particles. So imagine that you set up a laminar flow, right? And this is now water. And imagine that you had pennate diatoms. Right?
They're going to align along the flow.
Yeah. So you could align them by putting them into a laminar flow, right?
Could you do that differently for different particles? Like some particles maybe. No, there's not going to be anything that's magnetic in the ocean. So.
Iron particles are magnetic.
Are they? Those sound like with a magnetic field, that's around only half of the particles that are affected by that and not the other ones. So you could distinguish between the two.
Yeah.
Would that be in any way useful?
It is useful if you think about iron minerals in your, did I draw this backwards? I didn't draw that backwards, did I?
No, but it's just if it's in a laminar flow that's not no shear.
If there's no shear.
The difference between
Right, because they're in it. Okay. Right. I was like, this just doesn't look right.